So, good morning and welcome to the licensed defense of Eddie, Edward and Noyer. My name is Daniel Solmark, and in spite of what it says on the flyer, I am the main advisor of Eddie.
My mistake. Yeah.
No problem. I'd like to give a special welcome to some persons here that are here with some special functions today. We have the grading committee with Professor Mohamed Mousavi from Halmstad University, who is also the opponent of the thesis. We have Andreas Hermedal from Ericsson. We have Kristina Lundqvist from MDH as part of the grading committee. Additional advisors for Eddie are Paul Pettersson and Adnan Elsevic. So the procedure today, as the common procedure, is that Eddie will start with a presentation, talking about his work or presenting his work. After that, we will leave the floor open for questions for the main opponent. Followed by questions from the other members of the grading committee, and then we will open up the floor for questions from the audience as well. And that sort of concludes this part of the defense, and after that we will sort of find a quiet place to discuss the grading committee and the advisors, and during that time there will be some refreshments in Java for the rest of us. And once we reach a decision, or you guys have reached a decision, of course, we will let you know the decision in Java. So that's the procedure. We will also have video recording of the presentations, but there will be no video recordings of the questions from the opponents.
Yeah.
The grading committee.
Unfortunately.
Okay, so I guess that's...
Yeah, I can start. So thank you all for being here. And today, in 30 minutes, I'll try to summarize the main contribution in my licentiate thesis. If one sentence could characterize my endeavor, is the following: tool-supported automatic test generation enables more efficient industrial software testing of function block diagrams. This statement has support in the results of the thesis, and I will show that. First, let us start with defining software testing. To this day, software testing is one of the biggest research directions in software engineering, with direct applicability in industrial practice. So Myers, in its well-known book, The Art of Software Testing, define it as an engineering approach to quality assurance, having the purpose of analyzing and executing the software in order to find errors. Since the beginnings of software testing, we have tried to address complexity and improve, in a way, productivity through the use of more smarter techniques and tools. In terms of trends, we have progressed from testing software in terms of low-level functionality to automatically generating tests to the system as a whole, from structural testing via data flow testing, model-based testing, automated test generation, mutation analysis. In a way, testing software is arguably becoming more advanced than the software we actually produce. And I want to show some trends here. So if we start with 1970s, one trend was that software testing was mostly conceptual and was seeking to explore phenomena. On the right side, I have some examples. I don't think I will go through them, but just to show some example of papers and contributions that were related to this kind of trend. For the first one, in 1971, Richard Lipton proposed the initial concepts of mutation as we know it today. In 1980s, software engineers built new tools and methods. So it was something that there were more tools, more methods in software testing and software engineering. In early 1990s, software testers used their tools to run experiments. In late 1990, software testers used statistical analysis on data they gathered from experimented with their tools. In early 2000s, software testers ran experiments on real software. And then in late 2000s, software testers work on problems that industry cares about. As time has progressed, software testing research provides, in a way, a case for technologies, methods, and knowledge invoking changes in companies. And I think this is just a trend. And of course, you'll have papers now that will produce a new theory, and that's really good. But you'll see a trend that a lot of people actually do work on problems that industry cares about. I want to step back a little bit and look at the big picture of software engineering. And one way to do that is to look at the typical development process. The V model is arguably the most well-known process that evolved over time and supports, in a way, flexibility and also agility, in a way, into development process. It's a highly disciplined approach. It promotes design, development, and documentation necessary to build software. And our focus in this thesis is related to unit testing, where software is developed during module design phase. So this step is executed to eliminate bugs at code level or unit level, and is the smallest entity of software that you can find and can independently exist. So unit tests ensure that the smallest entity or can function correctly when isolated from the rest of the code and units. Another way to look at this is like any other engineering disciplines today, software testing use models of the system under test. So you have many notations from like formal mathematical description of the software to semi-formal notations like the unified modeling language. Historically, using models to aid software testing has played a minor role in software engineering practice. And within the last decade, model checking has turned out to be a useful technique for generation of test cases. So you could see this thesis in this way. You have model checking on one side. You have one particular model checker called UPAL, which is a tool for formal verifications, for formal verification. And on the other side, you have software testing and test generation. Basically, our thesis is the research focus is model checking for test generation. And we'll focus in the entire thesis on this issue. I will go first to the, secondly, not first, to the research method. So PhD students are expected to make an, in a way, original knowledge contribution and need to justify the research method and design to convince their audiences and also the examiners that such contribution is reliable. So this should involve not only the technique depiction in obtaining and analyzing data or something like that, but also the understanding of knowledge and how it's generated and developed. So Neil deGrasse Tyson, a well-known scientist, said the following, is do whatever it takes to not fool yourself, period. That's the scientific method. I know it's a statement that is simple, and in many ways it's simplistic, but it makes a difference when you actually think about it. To explain this better, in 2012, a research-driven collaboration was established between Bombardier Transportation, a large manufacturer of trains, and Mellard Allen University during the ATTAC European project. To show how we performed this research until now, we can have a look on a model for technology transfer in practice. This was published in IEEE Software in 2006 by Gorshek, and also Stig is also here. It's incredible how this model reflects how we approach the research even before knowing about this model. So reality actually it's integrated in this model somehow. So our research started with finding a problem or opportunity, and this was in collaboration with Bombardier, and it ends with proposing a solution for that problem while building knowledge in the area of test generation. So you can have this problem formulation where you actually formulate the problem and you do a study of state of art. Then you propose a candidate solution, which is between academia and in industry. And then you have a static validation with interviews, with seminars. You pilot it in a way in the industry. And then you do a dynamic validation where you release an implementation into industry, but it's still open to small changes and additions. And then we release the solution. Even if you look on the papers in the thesis, you would see that this actually it can be seen in the method and in the tool. We always had stuff to add on static validation and dynamic validation. Okay, so the results of the research is a collection of papers. So you saw that if you didn't took one, you can take from that table. It's with the word cloud on it. You cannot miss it. So the papers included were in peer-reviewed publications. So the first one in the International Conference on Software Testing, Verification and Validation Workshops. The second one is in the International Workshop of Combining Modeling and Search-Based Software Engineering. The third contribution was published in Proceedings of the International Conference on Testing Software and Systems. And finally, the pièce de résistance, as I call it, was accepted for publication in the Springer International Journal on Software Tools for Technology Transfer. And if you look, it's actually chronological also. So we wanted to have these papers in a chronological order so you can see how this method and tool evolved. So as I said, this thesis addressed issues related to model checking based software testing for function block diagrams. And it was conducted within the ATTAC project that started in 2012 by 15, I think, European partners. And the title of the project was, "The project aims to develop and enhance and deploy high-performance methods and tools for automated quality assurance of large and distributed software-intensive systems." It sounds quite dramatic, I would say. But the results presented in this thesis were strongly related to this ATTAC project. And at Bombardier, during ATTAC, we have identified some needs. And this needs that the engineers, while testing the function block diagrams, they must convey to a safety standards that mandate some coverage measurements. And also before this thesis, this was done manually. And I would say this was inefficient, so we could actually improve it. And these industrial needs drove us to use logic coverage, which is a concept that I will explain later, and to use a model checker and use automated test generation to try to solve these needs, these problems. To ease into the thesis, we need first to have, I think, a look on what's the software we actually test. So Bombardier and other companies are using for programming their control systems a language called function block diagram. And the motivation for using function block diagram is that it's the target language it's a standard in many industrial systems, and such as the ones in railway transportation domain. And it's a graphical, as you see, programming language based on element composition. So it's a component-based systems in a way. And FBD is used, or function block diagrams, because it's useful within applications with a high degree of data flow between the components. And an example of a program that depicts a contactor control, it's shown on the slide. So it's composed of several functional elements and timing information, and the blocks are supplied by the manufacturer or defined by the developer or predefined in a library. So you can see some simple blocks like AND, select, and move, which are very standard, and FLT-DLI, which is fault delay, which is a component that is provided by the developer. So it's created by the developer. Basically, the model elements are equivalent to predicates, if you look closely, and instrumentation points shown in a circuit diagram fashion. So it's very, very low level. And the core functionality of FBD is then achieved by logic operations on input signals to output signals. I think we'll go more in details, but basically you read the inputs, and this could be sensors or other inputs from other programs. Then you execute the program, and I will maybe explain later how we execute the program, and then you update the outputs. This could be actuators or other outputs for other programs. I think I will explain more when I will go deeper in how we use this software. Okay, so logic, why you use logic coverage for testing function block diagrams? So one reason is that logical expressions can be easily derived from all kinds of software artifacts. So you have source code, modeling diagrams, specifications, so on. You can actually express it as a logical expression. So another reason for the growing use in practice is you need some type of logic coverage because they're incorporated in some safety standards. And many similar logical coverage criteria were defined, but with different terminology. And I'll try to just explain it basically like this. So you have a predicate or a decision to an expression that evaluates to a Boolean value. So you can see an example here. Signal Z equals signal A larger than 0, and signal B and signal C. And the decision is signal Z. So the result of all of this logical expression. And a clause or a condition is a predicate that does not contain any logical operators, like this condition here, this condition here, this condition here. And based on this, you can create a type of coverage criteria called decision coverage, and I will explain it later. Condition coverage, one that are more complicated but easy to implement. Modify condition decision coverage or MCDC, and this is mandated by some safety standards, especially in the railway domain. Now I'm going to something else, but this I think is quite important. Are we alone? And this can mean a lot of things if you just look at it. I don't think we're alone, but yeah. Before going into more details, you have, are we alone in the research of automated test generation or test generation for function block diagrams? And there are a couple of other universities that are working on this. So Korea Advanced Institute of Sciences Technology works on, some people there work on automated test generation by using an SMT solver, another solver for that software. Yonsei University from Taiwan, they use a model checker to generate tests for function block diagrams. I also have to mention Oldenburg University from Germany. They proposed long time ago, not that long, but I think 20 years, PLC automata, and that's a formalism for PLC software, for function block diagrams, and for other software that you can create for this kind of hardware. And they are trying to also have some test generation approaches now because it's trendy, I guess. Then Toshiba in Japan, they have an approach on test generation using also an SMT solver that works for Toshiba code. And also MDH, which is, I would say, a game changer in this area. So we came with a lot of knowledge and a lot of industrial experience because of this collaboration with Bombardier. Let's go ahead with the contributions in this thesis. Although this was considered before by researchers, there are few practical solutions, I would say, that can be generally be applied on in an industrial setting. So based on the above discussions that I had before, we can identify our general research goal as to enable the usage of an applicable automated test generation framework for function block diagram software. And some people can recognize this Puppet Master from The Godfather. So we had the overall goal, and then we just split it up to a couple of research goals that we can actually achieve something that we can quantify. So different perspectives that will get us closer to achieving this goal. First of all, the first research goal was, okay, if we want to actually generate test cases, we actually need a model, a formal description, or some type of model that we can search through it. So we developed a transformation to a formal description of a model for function block diagrams software. And the first research goal is, in a way, it's needed for the next research goals. And the first step was to have to look at the program and then try to transform the structural information of the function block diagram. So for each block, we create a model, an automaton, and the templates of components are included, and we list all the automata network and representing the function block diagrams. I have to mention here that we do a transformation to timed automata. And why we do that is that because we're using also UPAL, and UPAL supports timed automata, UPAL timed automata. And also because UPAL is one of the best model checkers that you can find. And I knew how to use it. So that was not because of someone said, or because we just use it because it's really good. So we had the structural information that we transformed. And, okay, I think I'm going quite fast. So then we had input signals and output signals and blocks that we needed to transform. And we actually have every function block diagram that has input has a name. So we preserve this during translation. And however, it is often the case that signals in FBDs are not named. So if you have this example, the compressor start enable, you have wires here that are not actually named. So in such a case, the name given to the signal corresponds to the name of the block, which produces the signals. For example, the output signal produced by function AND, here 2, it's AND2, until it gets processed to the outputs. And then you have a lot of variables used for recording information in the model, and that's like read, execute, and write. Synchronizations that are used to hard code the execution of the program. Then in step 2, we actually had to transform the cycle scan and triggering, because the program, a cycle starts when the automaton enters the read inputs node and ends the computation when you update the scan time. So for a program, you execute the operation of each block, and then you have the connections between those blocks. So you have like a program composition with a set of interconnected blocks under a specific execution order. So basically here the execution order will be that you execute when you get the inputs for all here, and then you execute AND. So then you can execute full delay. And then you can execute AND, select, and move. So you have an order of execution in the program. In this way, you ensure that the blocks are executed one by one. And after the last block is evaluated, the counter is reset and to repeat the cycle scan. So you have multiple executions of the program. And the last step, and I think the most important one, is the block behavior integration, because we took into account the structural information, how the program executes, but we didn't say anything about how these blocks inside, how they behave. So we translated simple function block diagram blocks into predefined UPAL operators. So like the logical operators blocks are translated using the logical operators like AND, NOT, OR. And then you have arithmetic blocks that you translate using arithmetic UPAL operators. And then you have comparison blocks, the same. And then you have selection blocks, like this one, select, where you use if, then, else statements in UPAL. And I think I showed them here. Yeah. To give an example on how this could look, you have here an AND block. So basically the block is, the behavior is mapped. You have a block that is initially in location waiting, and after performing the read action, it starts executing until its internal computation is done. After completing the write action, which forwards the data from output ports via connections, the block becomes waiting again and waits until it gets its turn. You can have other blocks that are more complicated. So you can have bistable blocks like latches, SRS latches, and also other blocks that you can create manually, and then you need to transform them also. So other blocks are counters, timers, custom blocks that are implemented directly from the C-like implementation of a block. So if you have the implementation of the block in a language that you can transform it to UPAL, timed automata, plus the subset of C that is using. I will show a demo, so we'll see how it looks, how it actually looks. The second goal was, okay, so we start with what we contributed in research goal 1. So we have the transformation to a formal model, to a timed automata model. What we are missing is to demonstrate the use of a model checker for testing of function block diagrams. So we want an automatic test generation approach. So basically, in this research goal, we generated test cases for logic coverage for function block diagram programs using UPAL. So we make the use of the model checker ability to generate test traces witnessing a submitted property. So you can see that we can encode, we annotate the reachability property or the property to be checked, and we annotate also the model with the variables, and I'll go into details about that. And the last step is using UPAL for test generation, but UPAL is not a viable tool. It's a viable tool for model checking, but it's not directly tailored. It's not good for test generation in practice if you want to use it like that. So we demonstrate to work around this by automatically generating traces for logic coverage. So we propose analyzing the logic coverage as follows. So you annotate the conditions and decisions in the program. And then you formulate a property for logic coverage that will actually satisfy those. And then you find the path, the model checker will find the path from the initial state to the end of the FBD program. And decisions can be identified from the instrumentation points in the program. So you could see that you had in the previous program an end block, so that's a decision. And other blocks can be seen as decisions. Going back on different type of logic coverage, you remember decision coverage, condition coverage, and MCDC. Decision coverage requires that each decision evaluates to both true and false, not necessarily in the same execution path. And we implemented that into the model. Condition coverage requires 2 test obligations for each condition in a decision so that it evaluates to both true and false. And then you have a more complicated coverage criteria called MCDC that imposes 2 requirements for test cases. For each condition in the decision, test must show that the condition determines the value of the decision. And each condition has to evaluate to true and false. Yeah, but I think now enough talking. I think let us see the demo of the tool that implements this test generation technique. And it was developed here at Mälardalen University and is based on the collaboration we have with Bombardier Transportation. And the design of the user interface was to meet the exact needs of an industrial end user. Although there is a possibility for fine-tuning, in a way, the configuration parameters of the model checker, most of them are set to default values, so making the tool immediately ready for use. Actually, for people accustomed to UPAL, maybe they will be surprised not to see the user interface at all. So in this way, the user do not need to learn anything about UPAL or the model checking approach. So let's go. Let's see if it works. Works. So what we have here, and I think I have also my mentor and manager from Bombardier here, so I think it's okay to show the development tool that some people, the engineers at Bombardier are using. And this is called the 1131 tool, Mitrak, and you can create this kind of diagrams that I showed before. So basically this is a unit, a program that we want to test. And I think I opened here 3 programs, but let's go for this one first. And I think I will need to open it first. By mere surprise, I have it here, prepared. So you can actually see it here. you have a description of the program in the tool. This program is the fan control. So basically you have one input that is integer, and based on the computation here and this constant, you will decide what fan to actually pick, to be true or false, or what kind of mode the fan is, high, low. So you have one input and multiple outputs. So what an engineer will do in a general case, it will try to do decision coverage. And I will actually put, let's see, some trace. So we try to generate tests that will satisfy that criteria. So we'll to generate a test that will have 100% coverage for that program. It actually works. So basically what you see here, you have on the left side the steps that you can introduce into the program to test it. And if you see at step 1, the program says put input 9. In the second step, put input 4, and so on until you get 100% coverage. What we have here, we have an example that we generated 6 steps. So here the parameter was sum, like sum test. And what we want in some cases, this was default, was the shortest. Let's go for the shortest because I will show later why. So we want 4. So this is the shortest test that the model checker can give in order to have 100% coverage. On the left side, you have the inputs here. And here you have the outputs. But everything is false at the beginning. You see that it's false and you say, oh, this shouldn't be like that. But what an engineer will do here was based on the program and based on the specification, he will try to actually modify the outputs so that you can see there the expected outputs. So basically it will have, let's see if I remember this. This is true and this is true. I don't think it's correct, but let's go like this. And then you can validate tests. And it wasn't correct, so I have bugs somewhere and I know where. Basically what the tool shows you, the outputs, you have the expected outputs and also you have the actual outputs. And when you compare those, you see that with green, that the expected outputs and the actual outputs are the same. But with red, you see that there is a difference. So there is a mistake somewhere in the specification, there is a mistake in your program, or what we don't want to hear is there is a mistake in the tool.
You did a mistake, right?
For sure. So basically, in this case, this program is correct, and everything should be true here. But I didn't read the specification or didn't look on the program. This is one use case that you can use for this for this tool, and this is how it's used nowadays by some engineers at Bombardier. But let's see. I think I have time. Hopefully, yeah. I will go fast. So you can actually, this is a really cool feature. So you can open some manual tests that some engineer has. So maybe he wants input 8 and input 5 because he knows those are important. But if you look here, decision coverage will give you just 85%. Maybe you want more. What to do? So the tool is actually smart now to fulfill coverage. So you click this one, and it will add 2 more tests in order to get 100% test coverage. This is quite cool, and this is quite useful, I would say. But this was for this program, and I don't know if I have time to show more, but we can go back afterwards. But I have other programs that we can show. Let's see if I'm not doing a mistake. It actually works. And these are more inputs. I can validate them. So just to let you know, every step in the program is in sequence. So you have to put input 1, this step 1, to introduce these inputs, observe the outputs, and then introduce the next input. So the sequence has an order. So you cannot actually use input 1 and then input 16 because you will not have the same outputs. It actually counts the order. I don't know if I need to show anything else, but we can go back to the tool because it's here. Come on. This will take a while. Yeah. Okay, so you can actually download the tool. So it's freely available for academic use at completetest.org. The name of the tool is Complete Test. I actually didn't say that. It sounds nice, Complete Test, or Completest if you want to go for that. And you can download it and let us know what you think about it. I think it can be useful. Okay, so we have this in place. We have this tool. Now, what can we do to actually support tester and developers when testing function block diagrams programs? And we, in practice, so we formulated a third research goal as follows. So how we want to evaluate the applicability and the usefulness of the proposed framework in an industrial context. So we first look at as a really important question, and that is efficiency. What is the time required for the tool to generate tests that satisfy different type of coverage criteria like decision coverage, condition coverage, MCDC. And the industrial system studied in this thesis was developed by Bombardier Transportation. It's called TCMS. And this research, we have used all the programs written in the function block diagram language, standard language, resulting in a total of 157 programs. Each of the programs is sizable and representative of industrial program units used in the train system development. So some people would say this is quite small, but you have to keep in mind that engineers have to test that manually, had to do that before. So it was a reason why they needed to be like this. But maximum per program, you can have 32 blocks, 15 inputs, 29 outputs, and 196 decisions. So for each program, the tool generated a model version in Opal. Then for each implementation of the program, the tool generated test input vectors for 3 different coverage criteria. And the tool terminates the generation time by determining the coverage requirements satisfied by each test. So we have in the table here performance figures in terms of time needed to generate tests. So the generation time for MCDC, you can see average approximately twice as long as decision coverage. So we can observe that a few outliers in a way cause the average generation time to greatly exceed the median generation time for all coverage. So you have the difference between median and average. It's quite big. So you have some outliers there, programs that took a lot of time. But still fast, I would say, in average. For 34 of the 157 programs, the tool did not terminate. So after running for a substantial amount of time. So after discussions with engineers from Bombardier regarding the needed time for a tester to provide a set of tests for a desired coverage, we concluded, let's say 10 minutes is quite okay to have a reasonable cutoff time for the model checker. So you stop it and you terminate the search and get the test that is there. To determine the circumstances under which the tool does or does not successfully generate tests, we went to this type of question. How does the tool generate tests that achieve 100% coverage of each criteria? So how close the tool did come to generating tests? So we have 2 cases here. When the model checker finishes its execution, case 1 in the table, and the case when we forcefully terminated the tool because the running time reached 10 minutes. So case 1 consists of 78% of the programs, and case 2 has 22% of the programs because it didn't terminate. And you can see also the average coverage achieved for those 22% that didn't finish. For example, for decision coverage, you have 82% of the coverage already generated. If more data on this, so the number of decisions in the program for case 1 range from 1 to 22, with the average being 5. And in contrast, for case 2, the set of programs for which the tool exceeded the allocated time, you had the number of decisions in the program was between 12 and 196, with the average being 38. So this just indicates that as the number of decision increases, the performance deteriorates. So you have the cost of using the tool become prohibitive. This factor contributes to a scalability issue, which results in longer test sequences, especially when generating tests for MCDC. But engineers from Bombardier indicated that their certification process involved achieving a minimum of 80% decision coverage, for example, for all programs. So basically, in average, for decision coverage, we obtain 82%. And most of the programs had over 80%. So that was quite good. But we had a couple of programs that we needed to investigate further. And now I think I can actually conclude what I wanted to say in this the first part of the seminar. So in summary, the main contributions of this thesis are proposing a translation of function block diagram into a formal model, UPAL timed automata. We show an approach to generate tests using this model checker, UPAL. We show how logic coverage can be used on function block diagram for test generation. And we implemented a tool called Complete Test. And how I like to say it is the world's first test generation tool for function block diagrams, freely available for practitioners and researchers. I know it's a small world, but it sounds good. Yeah. After the first test generation tool. So it's a lot of words. But we carried out an extensive empirical study with these real programs developed by Bombardier, and the results show that model checking is suitable for handling logic coverage for real-world function block diagram programs. And also we reveal some, like good researchers, some potential limitations of the tool, so we can do research further. No, but because they're actually there. So the evaluation showed that the toolbook is efficient in terms of time required to generate tests that satisfy logic coverage, and it scales well for most of the programs. I think it's a positive and useful addition to testing function block diagram programs. Also, some internal results from Bombardier, and I hope this is okay to show, because this was results of the ATTAC project, and it was a byproduct of this thesis. These results are not in the thesis, but they're based on internal evaluation from Bombardier. So code coverage for unit testing can now be measured and documented. It couldn't be done before in this way. The increase is at least 40%. Efficiency, in a way, by using this tool, we reduce the number of engineering hours for unit testing. So you define test cases, you test, you document by 80%. So resulting in a reduction of total test time from unit level to system level by 20%. And this tool has been tested in the project called Zefiro Italy, and it's an Italian high-speed train. And the complete test tool is now rolled out in 2 ordered projects, C30, Stockholm Metro, and Hamburg commuter train. So the future is quite exciting. And now we get to the future. So we are currently investigating the approach on a larger case study in other companies maybe, or also in Bombardier more programs using function block diagram software. We look also on the test effectiveness, because we measure coverage and we say how close to the coverage we gain, but that's just a proxy in a way for how effective or how many faults we detected. So maybe we should look for fault detection capability and also use mutation analysis. That's a useful technique to measure the test effectiveness. We also need to understand how its usage in practice can vary depending on human and software process, because people actually use this tool, and we want to see how and what are the mistakes that they do or the tool does. But at the end, we need to actually improve the test efficiency by evaluating other approaches like search-based techniques, meta-heuristic search in combination with model checking and static analysis that can improve the test generation efficiency. Yeah, don't forget to download the tool. I don't know, I put it again. It's not that I'm earning money, but yeah. Thank you.
Rushing to do that, you just keep seated a while and we'll listen to some questions from the opponent. So thank you, Eddie.
Yeah.